Is 15 okay? Not sure. I hope it is. I hope it is. Okay, so if the music's too loud or too low, let me just focus a little bit. Yeah, that's it. If the music is too loud or too low, just let me know. Cool. Okay, so we are live. Let me see. My hair's kind of weird today. I don't know why. Like I have this curl here, but nothing here. Like my hair is just a little bit of a mess. Okay, no worries. So let me see if first of all I have to send the check-in. So please check in here. Cool. Okay, that should be it. Let's see. Nice. Okay, so welcome to Intro to Neural Networks with Tensorflow. My name is Charvel. Okay, people call me Bully. Hey, I love your hair. Thank you. Hey, it's Quakers and cheese. Thank you. Recently cut it because yesterday I graduated, so needed good hair for pictures. But yeah, hey, 404. Cool. So, intro to neural networks with TensorFlow. A little bit about myself. I am a robotics and telecommunications engineer. Hey, thank you so much. Yeah, it was awesome. Like, I have the diploma right there. Feels weird. Feels like, I don't know, too professional for me. Hey, hello. Cool. So yeah, that's about it. I'm a robotics and telecommunications engineer. I'm also a pod leader at MLH, and I'm a streamer. So yeah. We'll be starting the production engineering fellowship next week. So interesting week coming. But yeah, that's a little bit about myself. And yeah, let's talk about neural networks. So by the way, we're going to, going to use this stage. That doesn't look good, does it? Yeah, that's way better. Okay. I'm going to use Google Colab. Okay, so everything's on Google Colab if you want to follow. I forgot to upload these two notebooks to my GitHub, but I'll upload them shortly after our stream. Okay, cool. So just drink a little bit of water. There we go. Okay, so let's start. For people who don't know what neural networks are, it's a fancy term for a very fancy thing that humans have come up with recently. Let's just dive into it. Like, first of all, what's AI? Like, we have listened and heard like, hey, AI is doing lots of things. AI is just, all over the place. We're generating text, we're generating images, we're generating voices, sounds, music. And it's pretty cool. Like, it's pretty cool. It's a lot. But what does that mean? Like, what's AI by itself? Well, AI is a branch of computer science focused on creating systems or machines that can perform tasks that usually require human intelligence, without just reading about it. What does that mean? So AI is basically something that we can program for it to perform something that usually we did. So basically automating stuff, okay? Quick example of what an AI can do. From a simple task of reading an email and saying like, hey, this email is spam, or this other email is not spam, okay? From recognizing simple patterns to more complex patterns in emails, all the way up to generating text, or let's just assume like in the industry, let's say you have a factory and you are, I don't know, recycling. Okay, so it's a recycling factory. My voice is low. Okay, thank you. Let's see. Let's see how can I change that. Settings, audio. Is that better? Seems to be good for you. 404 looks good for you. Okay, so I just like added a little bit more volume to it. I don't want to like just take over the music and all. But yeah, I hope that this like is better. But yeah, cool. Okay. And thanks 404. Okay, so you have a factory that recycles and you want to know the difference between, I don't know, a bottle of pure plastic or a glass bottle. Okay, so an AI with computer vision can tell you that. Okay, and you can automate that in an insane speed. Okay, cool. So these tasks include understanding languages, recognizing images or sounds, making decisions, and learning from that. Okay, probably try to reconnect. I hope that check your volume. Sometimes it happens. Maybe I don't know. But yeah, cool. So take a look at this image. Okay, so this image shows that AI is a term that englobes or basically means or takes over everything that we can say, hey, a machine is thinking. Okay, but AI is not the correct term for. Okay, cool. Quakers, I'll do that. Thank you. Let's see. Probably up to 10. 5 notches down. There we go. Hope that's better. Cool. So we have AI that, basically talks about everything, machine learning and deep learning. So what's the difference between all of those three? AI can be something that basically does or basically doesn't learn from itself. Okay, perfect. Thank you. Thank you, Quakers. So basically, let's say, hey, I want to filter some emails from spam to not spam. You don't need to learn that. It's just, hey, find this pattern. If it has this pattern, voila. Okay, you can do that in a more complex way so that the machine learns by itself. So based on some fancy math that we'll talk a little bit later, you can have the machine learn. Deep learning involves neurons. Okay, so mathematical formulas that we'll basically dig into today that help the machine learn from specific patterns that we do not specifically mention. Okay, so our project, the last project, will be recognizing between cats and dogs. Okay, the machine will do that by itself. It doesn't mean that the computer will know, hey, this thing is a dog. Like the computer doesn't know what a dog is. It'll just, check patterns and say, hey, this looks more like a dog. This looks more like a cat. Okay, does that sound good? I hope it does. If you have any questions, just let me know. Okay, cool. Now, what is a neural network? Like, hey, we're focusing on deep learning. What's a neural network? So a neural network is a type of AI designed to work like human brain. Basically, we take inputs. Okay, let's say a human being sees something, takes the input through the eyes, computes the input, and outputs something. Let's say the voice. Okay, so it's like I'm looking at this cup over here. So I see the cup, I computed the cup, and I say cup. Okay, does that sound good? So input, output, input, computation, output. Okay, that's basically what the neural network is. So it's made up of neurons, okay, which are basically, or like the basic fundamental units of a neural network that process information, okay? These neurons are connected together and work as a network, okay? So if we have, I'll show you like a quick note in a second, but you have three neurons connected to other two neurons. So you have there 1, 2, 3, 4, 5, 6 connections. It means each neuron is connected to the other two neurons, so on and so forth. Okay, cool. Now, we'll be trying to figure out, work with images. That's kind of something that I like to do. What do we do with image? So what's an image? So an image is basically could be three or could be one channel of pixels. Okay, each pixel has a value, and that value gives us the information that we need to see, hey, this is blue. Hey, this is green. This is magenta. This is, I don't know, white. All the colors of the universe. You can compute it with RGB, which stands for green, or R for red, G for green, B for blue, sorry, or grayscale, or black and white, which is 0, 1. Grayscale could be from 0 to 1 using decimals to basically say, hey, this is more of a grayish, whitish than a blackish. Okay, cool. So the steps that will follow is image is broken down into numbers of pixels. These numbers are sent through the network. Okay, so again, you see the cup. In this case, I see the cup. My brain, breaks whatever it sees computes that, each neuron adjusts to it, so it pays closer attention to some things and it ignores other things. And at the end, it says, hey, it's a dog. In my case, hey, it's a cup. So, yep, that's about it. There, here it is. Cool. So, each one of these are neurons. Okay. Each neuron has, I don't know if you can see this, it has a mathematical formula. This is called the activation function. The activation function takes care of saying on, off in a certain way. Okay, so just to keep it simple, we get the input. Okay, let's say that it's an image of 3 pixels. Okay, pixel 1, pixel 2, pixel 3. Okay, each connection has something called a weight, which is a number. Okay, from 0 to 1. That number will basically change whenever the neurons compute something. Okay, so they compute, it goes back, and then it changes based on the error. And that means training. Okay, so when we train an AI or a neural network, the weights and something called the bias, which is another number, which is not here, changes. Okay, and it kind of adjusts to, hey, let's say that we have these 3 neurons. Okay, so this one has 1, 2, 3, 4 inputs. This one has 1, 2, 3, 4 inputs. And this one has 1, 2, 3, 4 inputs. That's why it's called a neural network, because by a network, it's connected. Yeah, and you can see this, it reduced to 3 connections each. Okay, cool. Now, each one of these has an activation function. Each line carries a weight, a number. So let's say that for, I don't know, for a cat, this neuron will turn on like 30%. Like just a random guess. This neuron will turn on 0%, and this one 100%. Okay, and that'll affect how these understand what these output. Okay, sounds magical. I know. We'll take a look at this. Basically, they say, hey, if it's like 30, 0, 100-ish, then it could be a cat. So let's perform more calculus to see how that works. Okay, cool. So here we have the activation function. We have a lot of activation functions. We have ReLU, softmax, sigmoid, tanh. We'll take a look at 2 of them, which is ReLU and softmax. But yeah, we won't dive into other activation functions just because it's an intro. But yeah, you can see we have an input, a hidden, and an output layer. Okay, in this case, these are the inputs. Now, something, if you want to work with audio, computer vision for images, each and every single one of the neurons in the input layer has to represent or has to carry the value of each pixel. What does that mean? It means if we have an image of 2 by 2, okay, 2 pixels by 2 pixels, our input layer has to have 4 neurons. If we have 5, no can do. Like, what do you add to the 5th neuron? You can do some more fancy stuff that we won't do, but more fancy stuff to say, hey, let's just reduce the image, yep, to a certain level in a way that it fits our neural network. So when you give Google or ChatGPT or any other AIs or LLMs an image, in the back, they reduce it or make it bigger in a certain way that it fits their neurons. Okay, it like you can upload a selfie, you can upload a 3x3 image, and it'll work perfectly because they normalize that part. Okay, that's how it works. Cool. Next one, activation functions. There we go. Cool. So an activation function is a key part of the neural network. It decides whether a neuron should be activated, turned on, or not. Okay, or how much do we want a neural network to activate, basically. Okay, it introduces non-linearity, which means it's not like weights or numbers just going by and don't change at all. It basically says, hey, with this number, based on the error that we outputted, should go down. Hey, based on the error, this number should go up. Okay, we'll take a look at that in a second with all the math and everything. Okay, cool. Now we have this one, which is called sigmoid. Sigmoid is used frequently for binary classification, which is either a dog or a cat. Okay, and you'll see that we'll use this one because it goes from 0 to 1. Yep, so it can give us an output, a number between 0 and 1. And if it's like a number that's like 87 or 0.87, it goes more towards the 1, so it's like a 1. If we have 0.34, it's more of like a 0, so we take it as a 0, okay? 0 could be dog, 1 could be cat, okay? ReLU, on the other hand, is 0 if it's negative, or the number if it's positive, okay? And this one's used for our a little bit more complex classifications. This one is used more for output classifications, output neurons, which say, hey, this is 0, 1. These is used more for hidden layers, which is this thing over here. Okay, so sigmoid usually goes here. ReLU, softmax, 10H usually go here. Okay, softmax, it's also used in output layers. Okay, so the types. Okay, let's go fast. We have feed-forward neural networks, which is basically the most basic type because it just goes forward. Okay, it doesn't learn backwards, it just goes forward. Okay, used for simple classification and regression. Okay, we have the CNNs, the ones that we'll be working with, which are specialized for image and visual data. Okay, it uses filters to detect patterns like edges, shapes, or textures. Okay, used for image recognition, facial detection, medical imaging, blah, blah, blah. Okay, let's say, think of it as if your brain's visual cortex, basically. Okay, you look at a cup, you see a cup, you compute a cup, and you say cup. Okay, cool. We have RNNs, which are recurrent neural networks designed for sequential data with time and order. Okay, so you can use this for a video, for example. So you can use CNN plus RNN to remember a person that's walking. Okay, so in a frame, a person is, I don't know, in pixel number 34. In the next 3 frames, the person is in pixel number 55. So it can actually remember using some, magic. Let's call it math magic. Okay, think of it as having memory over time. Okay, cool. We have long-term short memory, LSTMs, which are a type of recurrent neural networks, but better at remembering information over longer time periods. Okay, handles long-term dependencies better. You can think of it as RNNs with a smarter memory. Okay, it's like chat when you come back like 4 days later, and it's like, hey, remember the question that I asked like 4 days ago? I want to kind of talk about that. And chat can do that. Okay, cool. We have generative adversarial networks, which are GANs. Never worked with GANs before. Made up of 2 networks, a generator and a discriminator. They basically compete with each other. One tells it, hey, this is not good. The other one says, hey, this is good, and they get better. Okay. Generator creates data. Discriminator tries to detect if it's real or fake. Okay. Used for deepfakes, art generation, data synthesis. Okay. Think of it as a creative AI that learns by competition. The competition is another neural network. Cool. Okay. I think it's voila. Yeah, there you go. Let's go with the math. Okay, cool. So that's the first part of it, okay? A quick intro of what we'll be doing. Let's see, where is my... There you go. Cool. Okay. So, first of all, what are we going to do in this first part? We are going to try and create a neural network by scratch. No TensorFlow, okay? You'll say, hey, Bully, it says intro to neural networks with TensorFlow. Yes. Using TensorFlow is pretty easy. Debugging TensorFlow is not. Okay, you cannot debug either TensorFlow or what's Meta's one? Shoot, there's a counterpart for TensorFlow, which is Meta's. Okay, just forgot the name. But yeah, you cannot use only libraries. Try to debug them because you won't understand. Yeah, it's Torch. Thank you. Yeah, it's basically PyTorch. So you won't understand what the error would mean. Okay, so there are some errors that are too mathy. So we can say, hey, the output shape of neuron 32 doesn't match the input shape of the neuron 34, and it gives you like the whole matrix. And it's like, what's happening? So if you don't know what this means, you cannot fully work and fully understand how TensorFlow or PyTorch work. Yeah, exactly. Thank you. So what you are going to do? If you have worked with computer vision, you might probably know about this dataset. Okay, this dataset is called the MNIST dataset. Okay, internet is doing its own thing. Come on. Okay, there you go. Cool. So can you see this? These are zeros. Okay, the MNIST dataset is a whole dataset of images of 28 by 28. Okay, fairly small images with handwritten digits from 0 to 9. Okay, we have a lot of them. We are going to train a neural network from scratch. Okay, no PyTorch, no TensorFlow, pure NumPy, pure math. Okay, to recognize the digits. Okay, that's what we're going to do. Okay, so let's go to Colab. Part one. Here it is. Okay, by the way, no, this is not the first one. Wait a second, this is not. Let's open Colab. Let's open it here. File. New node we can draft by now. There you go. So let me open my cheat sheet because I don't know it by heart. So let's see Safari. There we go. Cool. Okay, by the way, the first thing that I'll say in the first disclaimer is it's been a long time since I've like gotten back to the pure math of AI or basically deep learning. So this first part will be based on Samson Zhang's video. Okay, great video. Here's the link to it. I'll upload all of this to my GitHub. Okay, but yeah, great video. I like this first part is based on that video. Okay, so cool. Let's start with it. Okay, so let's import things. Import num I as np. I'll do that. Is that better? I hope it's better. Cool. Okay, import numpy as np. Let's import pandas. Let's import matplotlib. Oh, I'll just leverage a little bit the autocomplete there, but I'll try to always write everything. Okay, cool. So let us connect to. We don't need a GPU for this one. Okay, won't change anything. Leave it as a CPU. Okay, so if you go here and you click on change from type, you have a CPU option. You have a TPU options. Here it is, sorry. And this is a GPU, T4 GPU. Okay, let's not use this one for now. Okay, let's use the CPU just because we don't need it. Okay, cool. So if you hit Control Enter, it runs the cell. Basically, it gives us like this. Okay, cool. Get rid of this. Let's create another cell. Okay, cool. Before that, okay, also before that, you have to have a Kaggle. You have to have a Kaggle JSON. Okay, so if you don't have a Kaggle account, create one. Okay, you go to your profile, and then where was it? Thank you. You'll see that there's basically nothing. Here it is. So for the API, create new token. Okay, it'll give you a JSON file. In that JSON file, you have to use it. Okay, because we're going to leverage a Kaggle dataset from a competition. Okay, so it's easier to just import it to the notebook. So for that, I'll use my key, not Kaggle personal. Here it is. Shoot. There it is. Cool. Yeah. Cool. Okay. So if you want to use Bash, okay, if you want to get into the terminal of this machine, you use the exclamation sign. Okay. So we'll create a directory. Should be. How can I? Wait a second. This thing over here. I'll get rid of this. Okay, cool. So I need a directory inside of here called .kaggle. Okay. Second thing is I need to copy. Just get rid of this so we can see a lot better. Kaggle.json. I'll copy it to this thing over here. Okay, so we have to add our JSON file here. Okay, cool. And we have to give it some permissions. So it's not 600. Shoot. Thingy Kaggle, which I don't know how's that called in English. In Spanish, it's called virgulilla. In English, it's like the little thingy there, like the little snake. And Kaggle.json. So we have to give it some permissions. Okay. Last thing, we'll use Kaggle competitions. Download. Okay. -c, which is because it's a tilde. That's a tilde. Okay, that's interesting. Because a tilde for us in Spanish, that's a tilde. Like the accent is called a tilde too. That's weird. Okay, cool. Thanks, Quakers. So download competitions. The competition name is digit recognizer. Cool. If everything's okay and you have your Kaggle JSON up, this should work. There it is. It says, oh, great. Let's first error. Competitions. Kaggle, is it correct? Invalid competitions. Oh, shit. There's an extra T here. Extra T always happens. There we go. Cool. So it says here downloading, and it's downloaded. As simple as that. If you hit it or click on your folder, you can see digit recognizer. Okay, it's on a zip file. Let's unzip that. So let's go into import zip file. How can I turn off the wait a second. I just AI assistance. No. Well, yeah, no. Thank you. Cool. Or zip file now. Zip reference equals zip file. The careful here with the capital letters. Zip file, and let's copy. If you click on the 3 dots here, copy the path, paste it here. Okay, and we'll open it in reading mode. Okay, cool. Now let's extract it. Okay, so zip ref, the extract all. Shoot, there we go. Into /content. Okay, so it's basically here. Okay, whether you imported the Kaggle JSON, if you don't use the Kaggle JSON, you cannot. Kaggle doesn't give you access to its basically to its data. Yeah, so you need a Kaggle account, which is free. Everything's free. Go into the API side, which again, it's if you hit settings, it's here. Okay, and it'll allow you to use the key. Yep, it's the API key. It's here. Okay, so you hit on create new token. It'll give you the Kaggle JSON. Upload it, do the whole thing, and it should work. Okay. If not, it'll give you an error like, hey, I'm missing key, or I'm missing like who the heck are you? Okay, cool. So yeah, into content, and then zip ref dot close. Okay, this should okay. Oh, thank you, Quakers. We should have our unzipped file. There we go. We have test CSV. We have train CSV. Sample submission CSV, which is from Kaggle. We won't use that for now. Okay, cool. It gives permission and it helps you. Yeah, that's it. It basically authenticates who you are. And some people use Kaggle for competitions, so you can have access to your competitions, your data sets, everything with Kaggle. Okay, if not, then Kaggle will just throw an error of unrecognized or unauthorized request. Okay, cool. Just close here because the air is pretty. There we go. The air is pretty cold. Nice. So this is good. Okay, this is good. Now, what will we be working with? Okay. So before we go into the math, let's just observe what's an image. Okay. So we got pandas. So let's do data equals pd.read csv. From here, let's do content. Instead of content, we'll have test CSV. There we go. And what does head do? It gives you the first 5 rows, or 10. Fine, there you go. Cool. So you can see here, this is an image. Okay? This is how a computer reads an image. Pixel 1 is 0. It's turn off. It's nothing. It's black. Pixel 782, it's 0, 2. So there are ones inside of here. Okay. That's basically the image. It's zeros, ones that represents pixels. Okay. Cool. Where do we start? Okay, like what do we do? So let's go to the method too. Okay. So our image is 28 by 28, which is 784. By the way, remember, 784 has to be a neuron in the input layer. Okay. So 784 neurons for this specific case. If we do 783, it'll throw an error. 85, it'll throw an error. It has to be 784. Okay, cool. Now, this is a classification. Okay, it's a classification problem. It's not binary. It means it's not 0 or 1 like dogs and cats. It goes from 0 to 9. It means we have 10 classes. 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Okay, so remember that because the activation function of the last neuron cannot be sigmoid, because sigmoid gives us numbers between 0 and 1, but we interpret them under 0.5 or 0, over 0.5 there are 10. I'm sorry, it's 1. Okay, so it's either one class or the other class. We cannot have multiple classes. Okay, so this is what we have. Okay, if you see, let's actually take a look at it again. This is our data. Okay, it's in rows. But how does a neural network actually look like? If we see here, it has to be columns, right? So everything that we have will transpose it. What does the transposing mean? What's that? Okay, let me just take this notebook over here. This is a matrix, okay? X, Y, it has values. Imagine this is an image. I want to transpose it. There you go. That's transposing. Okay, it means the rows are columns, columns are rows. Okay, cool. Now, instead of having the X value here, we'll have it as horizontal. I'm sorry, vertical. Horizontal to vertical. That's transposing a matrix. Okay, cool. So we'll have to transpose it. So we have the data like this. So each pixel fits each neuron of the input layer. Okay, that's it. First step. Second step is we are going to create a 2-layered neural network, okay? Without taking into account the input or the output, just 2 hidden layered neural networks, okay? Cool. So input layer 784 passes info to first layer to second layer to output layer, which will have only 1 neuron. This 1 neuron will only have an activation function of softmax, and softmax looks like this. Okay, don't freak out. Okay, it doesn't look really friendly. Let me just tell you what it is. It gives you numbers from 0 to 1. Okay, yeah, if you can see, neural networks love 0 to 1 numbers. They don't like huge numbers. We'll work with that too. So it gives us a set of probabilities of each class. In this case, we have 10 classes. So we will get a probability, like 10 probabilities. One will send out. We'll take the max, which is that one, and say, hey, it's probability number 4, which is 0, 1, 2, 3, which is number 3. Okay? If it's probability number 7, it should be 0, 1, 2, 3, 4, 5, 6. So number 6 stands out. So the neural network guesses that that's number 6. Okay? That's how it works. And this is the formula. Okay? E to the Z. Okay? Summing E to the Z, like the whole batch. Okay? Don't worry about the math. Just, it works. Okay? Cool. And here's ReLU. We took a look at ReLU. like a minute ago. Cool. Okay. So now we have to do something called forward propagation. Okay, which means I give you an image. From that image, do math magic, give me the output. Okay, voila, that's it. Okay, how does that work? We have the input layer, which is x. Okay, x is 784 times all of the images. Okay, so basically 784. Okay, this is the number of samples. Okay, we have the first layer, which is z1. Okay, z1 equals the weights, the number, the random number that we will first start with it and then tweak. Yep, times a. Okay, plus a bias. Okay, a is what we get here. Okay, so we are basically multiplying the weights times the first layer. We'll get something plus b, which is a bias. Okay, it's a random number that kind of helps the neural network not stay in the same number. Okay, so it's not linear. Okay, then we have the activation function. We have ReLU. This is ReLU. Okay, so what it does, it'll say, hey, remember, activation functions help the neurons turn on or off depending on the input. Okay, so first, like the neural network will do randomly. We'll try to guess. Okay, so we'll see accuracy of 10%, 15%, 8%, and then it has to go up because that activation function will activate either more or less depending on how important that neuron is, or actually those weights are to that neuron. Okay, sounds a little bit more magical. I know it works. Okay, cool. We have a Z2, which is the other layer. Okay, it's the weights times the activation plus a bias, and then we just output a softmax. Like whatever this gives us, give me the probabilities from 0 to 1 of 10 classes. Voila, that's it. Okay, it'll make more sense now that we code it, but yeah. Now, back propagation. We added an image, we computed the image, we have an output. When does the learning start? Well, let's go back. So now we have to go back, calculate errors, and based on those errors, we'll tweak the weights. Okay, so here it is. We have DZ2, which is basically the error of prediction. Z2, it's this output layer. Okay, it's A2, which is the probabilities, minus Y, which is the correct answer. Okay, and how does the correct answer, like, is Y a number 4? So if the correct answer was 4, will Y be a 4? No, we one hot encoded. It means give me the number of classes as a list, zeros to all the classes that there are not, 1 to the classes that it is. In this case, it's 4. You can see 0, 1, 2, 3 are in 0, 4 is in 1, 5, 6, 7, 8, and 9 are in zeros. Okay, so it means correct answer is 1. So ideally, this layer should have 90% accuracy. In this part over here, the error would be 0.1. If it said, hey, it's 90% a 2, and it's 1% a 4, then the error would be 0.99, because it's 1, because it's this minus 1. Okay, makes sense? Makes sense? I hope it does. Cool. Okay, now let's go back. Okay, it's basically going back. How much W and B contributed? That's what DW2 does. The formula is 1 over M times this thing over here times AT. Okay, what's A1? Remember what A1 was? The activation function, but transposed. Okay, because we're going back. So the whole thing just swapped. Okay, that's why we have to transpose it. Okay, it'll make more sense. I promise, I promise. DB2 is the error. Okay, so 1 over M, and we get all of the errors because we are summing all of the errors over M. Okay, cool. Now, DZ1, we go back to the first layer. How much was the first layer off by? That's the question that this part will answer. Will be W2 transpose, again transposing it, times DZ2, the dot product, into the derivative of the ReLU. It's a lot, I know. Okay, just trust me. I know you can. Just trust me. Okay, we'll have to derivate ReLU, which is pretty easy. Okay, cool. Then we get DW1, 1 over M DZ1 times the actual image but transposed. Okay. And then DB1, which just gives us like the average of the error. Okay. That's basically it. Okay. So it goes back and it basically does the same thing, but it undoes some stuff so we can get the actual error. Based on that error, the weights are changed. We can see here, hey, the new weights are the weights minus each error of each layer times alpha. It's too much. What the heck is alpha? Alpha is the learning rate. So imagine alpha as acceleration, okay? Or basically speed, okay? The more speed, the faster you travel, okay? Now, if you go too fast, it can be a little bit, very, not a little bit, but probably very unsafe for you and other people, okay? Because you're going faster. You'll say, hey, if I have to get to work fast, the smart thing would be to press the gas, like just hit the gas and just go. The correct answer is no. You probably have to accelerate at some point, but you have to slow down in other points. Let's say in curves, okay? So you're turning in a turning lane, you won't accelerate there. You'll just, hit a tree or something. That's what alpha controls. It controls how fast those weights change. But if you say, hey, instead of training 100 times, let's just train 10 times with a lot of alpha. It'll be the same thing that with the car and the tree. Like, you'll change so fast that you actually won't set in a good number. Okay, so the weights will just go from, I don't know, 0.6, 0.8, 0.5, 0.8, 0.6, 0.8. They'll never settle. So let's tweak alpha so that it settles. Makes sense? Of course, very small alpha, it means a very, very, very slow learning. We have to play with that, okay? It's called a hyperparameter, something that we as humans choose, not the machine. Okay, cool. That's about it. Cool, let's do it. So, no, not this one, this one. Okay. So, we know what we're working with, which is this thing over here. Come on, Mr. iPad. iPad and Collab are not good friends. There we go. Come on. Cool. So, this is a pandas data frame. Okay, let's change that to a little bit more or something easier to work with for math, which is NumPy. Okay, so let's do change to NumPy. So data NumPy equals input array data. Okay, by the way, let's change this one to train because we'll use this one to train. Okay, cool. So let's do that. Let's change data. There we go. Now let's shuffle. Okay, so now it's like as far as I know, it's shuffled. You can see that the label, this number means 1. Like this whole thing is 1. This whole thing is a 0. This whole thing is a 1. This whole thing is a 4. Okay, this is our Y. This is the correct answer. Okay, it's shuffled. Let's shuffle it again, just because. Okay. And let's shuffle. Okay, and let's do data. And there you go. Cool. Now, m and n equals data n. Let's get like the actual numbers. Okay, cool. Now, transpose. Okay, and we'll take a look at how this looks transposed. Okay, it means we'll just shift. Okay, cool. Data train, okay, equals data n. Let's just take, okay, in this case, oh, come on, there we go. The first 1,000, okay? Even though this is train, okay, we have more samples, we'll just use train. We won't use test, okay, cool. So let's just take 1,000 samples in n, okay? Shoot, sorry, yes, we'll do that. Give me a second. How do I do that? Can I do this? Does that work? I should zoom in a little bit more. Is that good? I hope that's better. Cool. Thanks for letting me know. Ooga Beluga. Cool. Okay, transposing is like this. Okay, dot t. Okay, cool. So, y train equals data train is 0. Okay, what does this mean? It means the first column are my answers. Okay, my y, which are answers, are here. Okay, so let's just store that. Okay, we won't give the neural network that. It will be just cheating. So we have to keep those for the back propagation. Okay, cool. Now the X train equals data train from 1 all the way up to n. Okay, what's n? The y thing here. So it means from here, from this pixel 0 up until, I don't know, pixel should be pixel 783, but probably up until number, I don't know, 500. Okay, cool. Okay, so, and now X train equals X train over to Y. Remember I told you neural networks love to work with values from 0 to 1. We just assure, like we're just doing that, okay? So because it's a grayscale image, we are working from values from 2 to 255. 0 is black, 255 is white. So let's just regularize that from 0 to 1. Okay, easier, better for a neural network. Okay, cool. Nothing and m train that we're going to use equals to x train.shape. Okay, cool. Now that should do its magic. There we go. Cool. First part of the neural network. Okay, every single weight, every single bias has to be randomly assigned. Okay, that's how we start. We start guessing, and from there we tweak. Okay, now you'll say, hey, why don't we assign 0.5, 0.1 to each and every single one of them? Because you'll create a problem that when it tweaks everything at the same time, the same thing. Okay, so instead of, if we have everything in 0.3 and it tweaks each one of them 0.2 up, each one of them will be 0.5. That won't change a lot, like everyone's acting the same thing. But what happens if you have 0.5 in one weight, 0.1 in the other one? If you go 0.2 up, one activates more than the other. Yeah, so we can start and tweak. If not, it'll just do linear things, okay? It won't work. Cool. So let's see. We need params, okay? Cool. Now, W1, okay, familiar terms, np random, did rand, a number, come on, actually, sorry, media parentheses, 10784. It means give me 10 numbers, okay? I'm sorry, yeah, 10 numbers and 784, okay? This means a matrix, okay? Minus 0.3, okay? Just because, okay? Because we want to make sure that it doesn't create like the same numbers, okay? Cool. Bias, reverse bias is np.random dot ram 10 numbers, only one, okay? Minus 0.5. 0.5. There we go. Same thing. Okay, let's just copy paste. I saw it. There you go. MP. But instead of 1, it's 2. Okay. First weight, first bias. Second weight, second bias. And let's just return W1, E1, W2, and E2. There you go. Cool. Nice. And it params everything random. Okay, now let's start with, oh come on, my iPad is just doing weird stuff. ReLU, okay. ReLU gets a value and will give us the number. Okay, let's look at ReLU again. It was here. this is ReLU, okay? And here's a formula. It's the max number between 0 and z, okay? So we need the z value, okay? Cool. So, where's my, there we go. Cool. So, let me just try and scroll down here. Okay. Safari is just not good. We get the z value, okay? Now, return. Actually, yeah, let's go with the derivative too. Okay, so we have to derivate ReLU, okay? Remember here, this is the derivative of the ReLU. It means we have to undo the activation, okay? So to undo, it'll be easier than you think. If v, actually if not v, which is normal ReLU, should be np.max or max. I'm not sure. Give me a second. Because this could be a problem if I don't do it correctly. If not the np.maximum, okay, should be with numpy between z, okay, or z and 0, okay. It has to give us basically is this thing over here, okay, max between 0 and z, okay, cool. Now else, if we are derivating this, fairly simple, z greater than, actually, should be, sorry, greater than 0, okay, fine. Why is this like, why does this work, okay? If you are new to calculus, this will make sense. If you are not, this will make sense, okay? Like, if you don't get it, it's fine. It's fine. Like, don't worry. It's some calculus thing, okay? If we try to derivate a constant, the derivative of a constant is 0. Fairly simple. This is not a constant, okay? Like, this is x or z, okay? So we are saying, hey, return 1 if it's not a constant, return 0 if it's a constant, because the derivative of x, or in this case z, because it's a variable, its derivative, it's 1. But if we have a 0 as number, then, you know, you just get 0, okay? Yes, I'll share them. I'll share it right now. Why not? Let's do this very quick because I'm running out of time. Also restricted. Cool. Here it is. Nice. Very good. Cool. Okay. So running out of time because we have to talk about TensorFlow too. So this is ReLU. Okay. This is how ReLU works. We'll work with it in TensorFlow. Yep. It'll work. Cool. Now a little bit faster. We have to one hot, okay? Remember, one hot means doing this, okay? Why the name? I don't know. I'll give you permissions after the stream, okay? Yeah, I got the email. Just I'll focus on the stream and then I'll give you permissions, okay? Cool. Now, this is one hot. It means give me a 1 for every single number that it is, 0 for the incorrect numbers, okay? So for one hot, we'll get a y, which is y is the answer, okay? What we do is one hot y. Wait a second, let me just turn off the yeah, I'll give you permissions just after the stream, okay? Cool. Equals np the zeros. It has to be y dot size, so in this case 10, but let's do it a little bit more fancy, okay? Y size, y dot max, okay, plus 1. Cool. Okay. Now, yep. Okay. 1 dot y equals. I'm sorry. Actually, now we'll set the 1. Np dot arrange y dot size y, and this should equal 1. Okay, basically says in the number that is like the number that's correct, give me the 1, if not 0. Okay, turn this thing. Okay, cool. Now that's one hot. Okay, let's go with the next activation function. Softmax, okay? Softmax gets a Z2. Okay, let's not see. There we go. What is softmax? I cannot see it here. It's this thing. Yep. So e to the z over the sum of e to the z of every j. Okay. Go back. It's not as bad as it sounds. Okay. A equals np that exponent, which is the e in z. Okay, over sum of np x it's just simple. Okay, and then return a. Okay, cool. Now let's start with the interesting things. Okay, forward propagation. Just try to scroll again. There we go. Yes, sir. Did I? Diff forward prop. Okay. Cool. Now, forward propagation. It means I give you an image, compute the thing, give me whatever you think it is. Okay. I see a cup. I compute a cup. I say it's a cup. Okay. Cool. So, give me a second. Oh, come on. Will I have to? Yeah, I'll probably have to. I'll do this. Is it this one? Yeah. Because I can't scroll my iPad. My, Safari is not the best. Okay, cool. It should look the same for you. Okay, nice. So, let me just find it here. There we go. Cool. So, we basically are going to put this, okay, into Go. First part is Z1, okay, equals W1 that we have already. It's a dot product, okay, with X, which is the image, plus V1. By the way, here I missed it. We have W1, we have V1, we have W2, V2, and X. I see your requests. Okay, I'm not ignoring them. After the stream, I'll add you. I'll give you permissions to see the presentation. Okay, cool. Now that's Z1. Okay, A1 remembers activation function using ReLU. So ReLU Z1. Okay, voila. We got the image. Now we activate the neuron. Okay, Z2 follows the same order. We get W2, okay, which are the weights, which are the numbers, okay, that control the activation function, okay, dot, okay, A1 in this case, because it means this one is connecting to this next layer, okay, plus E2, okay, which is the other bias, and A2 equals max plus smaller letter Z2. Okay, it means activation function. I'm sorry, first layer, second layer is activation function, third layer, and now activated. Okay, and now easy. Return Z1, A1. Careful with the order because we'll use these to connect right now. Okay, go to my back. There you go. Voila. That's forward propagation. Okay, it means give you an image, I compute, give you an output. Okay, it says when you should make your own model like this versus using a pre-trained model. Ooh, that's a really good question. I'll answer it right now while coding. Okay, you have data. Okay, so the model by itself, it's not. Okay, I'll say something that's probably. I don't mean to offend any math people, okay? It's not that hard, okay, as it looks, to create a model from scratch, okay? It's a lot of knowledge, you have to know, hey, I know that this specific formula works to do this, it does that, okay? The hardest part of it is to get the data, okay? So let's say YOLO, okay? YOLO is, it stands for you only look once, which is a vision model, okay? And, oh, sorry. it can do lots of things. Okay, YOLO can detect cars, dogs, people, trees, whatever. Okay, you should use your own model when you think that you can tackle the problem. Okay, so let's say it's a problem as simple as MNIST. Okay, it could be a model that, I don't know, just looks for between a bottle and like a glass bottle and a plastic bottle. Definitely try to create it by your own. It takes time, okay, because you have to get the data, you have to write the whole neural network, test it, tweak it, and I'm not saying you can't. I just say it takes a little bit of time. Okay, so definitely use a pre-trained model, fine-tune that model whenever you have something more complex. Okay, why? Because in the end, you'll have to train the model, you have to get your data, but you don't have to do stuff from scratch like this. So it's like, when should I use TensorFlow when we're not? Like, try to use TensorFlow like a lot, or PyTorch, because this just takes time. It's not bad, it just takes time. Okay, does that answer your question? Cool, that was a question. Yeah. Let's do this pretty quick. One hot y equals. Now, remember, we have to get one hot first, okay, to calculate the error. So, one hot y. Now, remember, the z2 equals a2, okay, minus one hot y. Okay, what happened there? Okay, one hot y. There we go. Cool. Now dw2 equals 1 over m times dz2. We have to transpose it, because if not, it'll throw an error. Okay, it's a dot product of a1 with transpose. Okay, because we're going backwards, we have to retranspose everything. Okay, dv2 equals 1 over m times np, that's sum, and in this sum it's the z2. Okay, cool. Now that's dv2. Now dz1 equals now it's the weights that we got into transpose it, dot product, I know it's a lot, dz2, okay, whatever we got first, times, we have to undo the activation function. Really? Okay. Z, so z1. Okay, so it's a derivative of the activation function. We undo the activation function. 0 for 0, 1 for any other number. Okay, cool. dw1 equal 1 over m times ez1 dot x, okay, and db1 equals 1 over m times np, that sum again, but now of dz1. Okay, and we return dw1. We need this to reassign the parameters. Okay, dv1, dw2, and dv2. Okay, cool. Next block finished. Okay, third block. The parameters. Okay, we have to get. Okay, I'll just try. These are a lot, so I'll just, for time's sake, I'll do copy paste in this part. Okay, so we have to get w1 b1, w2 b2, dw1 db1, dw2 db2 alpha. Okay, remember, we have to do this part over here of the parameters. Okay, so the new w1, which is the weight, is weight 1 minus alpha times dw1. What was alpha? The learning rate. Okay, basically the speed that we wanted to learn. Okay, so let's see, w1 equals w1 minus alpha times dw1. Okay. Same thing for b1 equals b1 minus alpha times db1. What was db, or what does the d stand for? It's like for the errors, okay? Cool. Control C, Control V. Now I'll use something just to speed things up. How do I do this? If you select whatever you want to change, that repeats. Okay, so I select 2, Control D, gives me like the all of the repetitions. Okay, so it'll give me all of the 2s. Okay. Okay, my answer was it's basically not that hard, because you just weren't sure what the benefits of doing this compared to like an AI studio. Yep. Okay. Okay, and can be more customizable to different. Yeah. Okay. So the YOLO and all of those AIs, or like neural networks that are online that you can find and fine tune. You can fine tune them and basically train them also from scratch with your data. Okay. So the thing is, you can use YOLO. You can use all of those models. Yes, use them. It's easier, it's faster, and it guarantees that it works. If you want to create it from scratch, it can be probably because you're in a company that they're asking to create something like YOLO, for example, just an example, but for the company, with the rights of the company, okay? Because YOLO is open source, okay? So that could be a potential issue there, okay? So, it's up to what are you working with. If it's just like for you, just use something that's already created, and you leverage that people that know more and have already worked on that will guarantee that that model would work for you. Yep, cool. You'll still use your data, okay? You can either train it from scratch or fine-tune it. Fine-tune it, it's just way easier. But if you need some specific thing, use your own data to train the whole thing. But yeah, that's basically it. Yep, you're welcome. Cool. Okay, let's do it faster. Cool. Okay, db2, and I think that's it, right? Yeah. Okay. Return w1, v1, w2, and v2. Okay, cool. Now, to calculate like how the model is doing, we have to predict. So get prediction. Basically ask the model, hey, what is this? Okay. A2, remember, is the activation function neuron that has been modified or tweaked by the weights and biases. Okay, so the last neuron should be fine. Okay, so return np.argmax. Basically give me the biggest. Remember, we were using softmax. It's a possibility. Give me the biggest possibility that you think of. Okay, that's basically it. Okay, it'll give us a number. Okay, cool. Now, forget accuracy. Shoot. Now we have to get the accuracy between the predictions and the actual answer. Okay. So hey, thanks. Print predictions y. Okay, let's see what the heck's happening. And then return complete that sum. Okay, means give me the predictions over y that's size. Okay, is size a function? No. Okay, cool. It's basically predicting, getting the average, and saying, hey, from 10 predictions, you got 1 right. You are basically casing, okay? Cool. Now, I think I'll copy paste this whole thing just because I won't have time to go to the TensorFlow part. Okay, don't worry, this will be on my GitHub. Okay, I'll walk through it. So we have W1, B1, W2, B2, init params. Okay, did I call it the same thing? I think I did. Yeah, cool. Init parameters. So give me random parameters. Okay, voila. Now, epochs are the number of iterations that we wanted to train for. Okay, so we wanted to train for, I don't know, 10 epochs. The more you train it, the better it does, the better it learns. If you overtrain it, then you'll overfit. It means it overtrained with the test images or the training images that it basically does way worse with new images. Okay, that's how it is. Like that's how it is. Okay, if you tell a baby, hey, a yellow flower is a flower, and the only thing that you show that to that baby, a yellow flower is a flower, then when it sees a rose, it won't say, hey, that's a flower. It'll say, hey, that's not a flower. Like flowers are yellow, because you overtrained it. Okay, so that's how it works. Okay, cool. So we do the forward propagation. We get the values. Okay, with the values here, we get the back propagation. Okay, we update the parameters. So we get these new ones that'll be fed here. Remember, X is our image. And if, for per H10, okay, we'll get the iteration, we'll get the accuracy, okay, and voila. Okay, cool. Let's run this. No errors for now. Let's train, okay? Should be pretty fast. I'll train it. Let's do 20, okay? Errors, yeah, I knew. Okay, cool. Oh, that's not good. Okay, shapes. Okay, Z2, give me a second. Should be in back propagation. Give me a second. Yep, see, these kinds of errors appear in TensorFlow. You have to understand what do they mean, okay? It means something. I'm trying to multiply 10,784 by 10,41,000. Okay, so those matrices, I think I overtranspose or didn't transpose something. So let me just check back propagation. This one's transposed, which is fine. DZ2 dot, yes. Okay, I don't want to take too much time. If not, I'll just copy paste the whole code. ReLU, yeah. This is transposed. This is transposed, yeah. It's a dot. Did I get it wrong for a prop? I don't think so. No, it should be back prop. Okay, I won't take much time debugging. I'll just copy paste what I have in my cheat sheet. This should be it. Okay, hopefully. Great, it's not. Let's see. Oh, I think I know why. Wait a second. So it's in Z2. Let's see. It's getting it here. It's doing W2.A1. What? DZ2 said here. What? That's weird. In forward propagation, what? It's getting into forward. It means. Wait a second. Let's do this. Sometimes forward prop. Are these the same? Should be the same. Yep. Okay. I won't take much time. Just trying to figure out where I just didn't or had an issue. Let me just copy paste the whole thing. EW1, I don't think so. DW1, I don't think so. This one, nope. No, it should be transposed. You can try it though, but it should be transposed. Nope. Yeah, no. Cool. I'll just copy paste the whole thing. This will be on my GitHub. Okay, I'm sorry about this. I'm running out of time, so let's do one hot just in case. Did I get value wrong? Probably. I don't know. There we go. This should be there. 8 parameters. Are parameters okay? 784.1, 784.1. They should be. I'll just copy paste it. Just if. Okay. Should be the same. Yeah. I hope this works. Oh, come on. Not online. 48,000. Yep. It's trying to multiply this times this. Okay, we have a new error actually. Come on. Did I get softmax wrong? Shouldn't though, but let's see. Softmax. Okay, yeah. Get it? I get it. Cool. This was changed. Please. There we go. Cool. Okay, it works. What was it? I don't know. Okay. Cool. So, we did for 20. Remember, for each 10, we are just outputting the prediction and the accuracy, okay? It started with a 6% accuracy. It was it was just trying to like guess, like, hey, I don't know, is this a 10? I'm sorry, is this a 9? Is this an 8? A 0? Blah, blah, blah. After 10 iterations, it means in iteration number 20, 15%. Let's do 100. Did it pretty fast, okay? Let's see how it does. So 10% now, 16%, 23%, 31%. While it's training, okay, I'll copy paste. Nope, not this. Okay, I'm sorry. If not, we'll just won't go into TensorFlow and I'll be really, really, really sad, okay? Cool. There you go. 59%, okay? We have to train for more. I won't do it because of the time, but it will do better, I promise, okay? Cool. So, okay, I'll make the predictions. I get the image, weights, biases. I do one forward propagation. It means, again, I see a cup, I compute a cup, and I say cup, okay? That's what it does. Get only the last neuron, just because that's what we need. We get the predictions. Remember, it's softmax. We get the max number from that, return the predictions. From there, just test, do fancy stuff, and just show it. Okay, let's do that. Let's show for 0. Oh, what? Aren't they? What? The only one is not defined? Ah, cool. My bad. My bad. EW1. Yeah, you got it. Yeah, that was the error. No. Cool. So it shouldn't take time. And after that, we should run this. Okay. Cool. Let's just get the first image, the second image, third, and the fourth. Remember that we shuffle it here. So it should be random images. Okay. Cool. Oh, come on. Hey, better than last time. 63%. Okay. Okay. Cool. So, prediction. Okay. The label is number 2, and it's a 2. Well, that's not bad. Wait a second. No. It predicted 1. The label is 2. And you can actually see it kind of looks like a 1. Probably with more epochs, it would have learned it, okay? In this case, it failed. Ooh, prediction 0, and the label is 0, and this is a 0. Okay. Prediction 7, label 9. Okay, it thought it was a 7. And that's it. Okay, well, let's do more testing. Let's see, what if we do 10, 11, 12, and 13. Okay. 3, and it's a 5. Okay. 9, and it's a 7. Okay. 1, and it's a 1. So we can see that it learns. It doesn't do really good. It's 63%. Okay. More epochs, the time that we don't have. You can tweak alpha. Okay. We can tweak alpha. We don't have time. Okay, so tweak alpha later, tweak the epochs, and you'll see that it'll do better. Okay, just that. Same notebook. Okay, let's not take too much time. Now, how does this look in TensorFlow? So this looks chunky, too mathy, too complex, but we kind of understood some stuff, right? We have to be careful with the size, transposing matrices, okay? We have to be careful with that, okay? So, let's go with the second one. Here it is, just put it here, okay? Very cool. It'll be an animal classification. It means from dogs and cats, okay? Now, import TensorFlow as TF, okay? Cool. And let's import OpenCV, CV2, CV, just why the CV2, I don't know. Okay, cool. These two are needed, okay? Nice. Okay, in the meantime, the next code is actually getting the dataset from cats and dogs, okay? How did I get these datasets? Just Google, hey, I don't know, Kaggle dataset, dogs, cats, or whatever, and you'll get it, okay? Cool. Now, Kaggle datasets, download. Careful, it's not the same thing as we did before. The first one was competitions, okay? Kaggle does competitions. It gives prizes, Okay, so you can go and try some Kaggle competitions. You can win. I trust that you are really smart and that you'll do good. It doesn't cost anything. Okay, it just um, you know, it just if you want to have fun. Okay, generic code makes these subject. Okay, cool. Yeah. So careful here. It's not competitions. In this case, it's just a dataset. Okay, we download. It's from this person here, and it's called cat and dog. Okay, cool. In the meantime, let's unzip the data. Okay, we'll copy paste just because we're running out of time. Where is it? Here it is. Okay, let's copy paste the whole thing. I should have created a function. Ah, my bad. Cool. Not this. Instead of digit recognizer, it's cat and dog. Okay, so let's change this one to cat and dog. Okay, cool. That should be working now. We should have the cat and dog now. Okay, cool. Now, when you're working with AI, the most important thing is the data. If data is wrong, you can have YOLO, you can have the best neural network in the world. If the data is just wrongly labeled, the images are not good, the audio that you're trying to use, it's too noisy, it won't work. Okay, data is the key part of this whole thing. Let's take a look at that. Okay, import random, import OS. Okay, import mat. We have matplotlib, and actually import matplotlib that image as empty image. Okay, matplotlib there. Cool. Now we'll check an image. Let's do cats first. Okay. Let's do a return image, and you'll understand why. Okay. Do I have something more? No. Okay. Cool. So we'll just see if the image is like. Let's just take a look at what we're working with. So if name the local docs, then files equals. Wait a second. Is this the one that I'm talking about? Yep. Always that list here. Okay. Let's do slash content. Slash content means here. Okay. Slash training set. Why training set? Because if you open here, so this zip gives us a training set. From training set, we have another training set, which is weird. Yep. And then opening this, we have either cats or dogs. Okay. So slash that should be dogs. Okay. Actually, let's just do it fancier. Why not? Yeah. Why not? Like, if you want to be fancy, let's just be fancy. Like, let's just do fancy Python. Why do if else if we can do that? Like, I just wrote it. I just saw it and I was like, what? Why did I use an if else there? Okay. So length equals length of files. Okay, the number of files or images that we have. Okay, let's just pick a random image. So random, let me randoms. Okay, 0 and length -1. Okay, image equals np image dot read. Okay, and should be this whole thing again. Okay. Little thingy there. With name slash files in R. Yep, I saw it. Don't worry. You have to put the F here. There we go. Cool. This says, hey, give me an image or read actually the image in the name, which is either dogs or cats. And it's the image name. Okay. So it could be image 0001. That's it. Okay, cool. Now we get the image. Got the image. Now we'll probably need to return it later. That's why I have the return image. If not, we return image and PLT that in show image. Okay. Let's just print the image that shape. This will help us find the number of input neurons. Okay. Else image. Cool. Let's try. Let's see how this looks. Okay. By the way, I'll just there we go. Go check image with name equals. Okay. Actually, yeah, that's it. Okay. Okay. Interesting. We have. I got 405 times 500 times 3. What does this mean? X has 405. Y has 500. Actually, it's all the way around. Yeah. Y is this one. X is this one. And it has 3 channels. Okay? RGB. Okay? So we have something called a tensor. Okay? It's a matrix. And inside we have matrices. Okay? That's the easiest way I can explain out what a tensor is. So this is a tensor. It has 3 channels of this. 3 channels of 405 times 500. Okay, cool. Let's take a look at a dog. Okay. Ooh. Is it dogs? My bad. Sorry. Okay. There's a dog. There's a cute dog out there. We have an issue. 454, 47, and 3. The input neurons have to be static. We cannot change them. Okay. The number of input neurons have to be the same. Let's fix that, okay? Tensorflow is just great, okay? Cool. Now if I do this, does that affect you? Yeah, it affects you. Okay, cool. So, to add our data to a TensorFlow neural network, we have to import it and transform it into a TensorFlow data. Okay, let's do that. Train data. Generator equals TensorFlow.keras, the pre-process. Okay, it's pre-processing the image data generator. Okay, it means create something called a generator. Okay, that a generator, the only thing you can add more stuff to it. We won't see it today, but you can add noise to your images. You can, you can resize, you can do a lot of things. Remember that I said earlier, neural networks love working with numbers from 0 to 1. Let's do that. Scale equals 1 over 255 dot. Dot means give me the float number, okay? Cool. That's for the training part, okay? Now, to be able to learn, we need to test over a different batch of images. Okay, say I don't know, the teacher asks you, hey, how much is 2 plus 2? 4. And in the test, the only thing that she'll ask is 2 plus 2. Well, that's fairly easy, right? Like, you won't do bad, okay? If you were taught 2 plus 2, and then what's 5 plus 5? It doesn't test your memory, but the ability of you to compute a number. That's what we have to do. So test, validate, data generator equals df.keras. This image. Okay, the same thing, and we'll rescale it. Will equals. There we go. Oh shoot, my bad. What? Ooh, cool. Image data generate. Really? Did I get it wrong? TF.KRS. The preprocessing. Oh, sorry. It's dot image. Okay. My bad. Okay, cool. Now, next thing is, okay, we got the generators. What do we do with them? Let's flow the images to the generators to transform them into something TensorFlow understands. Train data equals train data generator dot flow from directory. As simple as that. It means I'll give you wherever my images are. I don't have to do anything. I'll just tell you what to do with it. TensorFlow will do that. Interesting. Let's do that. Okay. Directory equals this folder over here, because the images are just under it. Okay. TensorFlow will actually take the name of the folders and classify them as classes. Okay. As as cool as that. Okay, cool. So let's get the path pasted here. Okay. Now, what else can we do with this? Let's do a batch size. And it kind of performs weird, but trust me, it like I tested it because I created the whole thing. And it works good, and I'll explain why it kind of works weird. But yeah, so the batch size is basically how many images I can input into every single epoch. Okay, cool. Now that way it's faster and easier for the neural network. Okay, target size. Ooh, what is this? Equals 256, 256. So whatever image we are going to input, transform it into an image of 256 by 256. Problem solved. If it's an image of 1,000 times 1,000, it'll be a 256 by 256 for the neural network. Okay, cool. Now, careful here. Class mode. It means how many classes? Is it a binary? Yes, it is. It's a binary. It's not a multi-class. It's binary because we have only two, cats and dogs. Let's add a seed. A seed is for you for you to reproduce basically the same thing as me. Okay, because it uses random numbers, so the seed will give us the same output for you and for me. Okay, cool. Now, I'll copy paste the whole thing just to make it faster. Instead of train data generator, it's this thing. Okay, so copy paste the whole thing and change it. Okay. You'll see we have a training set. Do we have a test set? Yeah, here's a test set. Okay, so instead of training set here, let's leverage the control D. So select training, control D. We selected the two, test, and escape for to get the normal cursor. There you go. Cool. See, now same thing. Seed, class mode, 256 and 32. Okay, if we change this, it'll give us an error. Like, hey, I just have 256 times 256 neurons of input, but you're giving me images of 300. That won't work. Okay, we can let's look at the error later. Okay, it says here found 8,000 images belonging to two classes and 2023 images belonging to two classes. It did it for us instead of us doing it for TensorFlow. That's it. Okay, it did it for us. Does the target size affect the amount of accuracy? Yes. Well, it could. Okay, it depends on. Yeah, so okay, the answer is yes. Okay. Lesser size, lesser what's this word that I'm looking for? It detect or lesser size, lesser the image quality, thus lesser small things that the neural network can look at. So you are sacrificing some small things. I just can't get the name. I just can't get the word. It's the details. Oh yeah, that's it. So less detailed the images, faster the neural networks does, less computation time and expense, it kind of loses some detail. Okay, because in this case it's a very, let's say, simple or very easy to see the difference or tell the difference. We don't need that much like detailing in the image. Now if you want to see or classify between pugs and bulldogs, you'll probably need a bigger image so that you get more details. Okay, okay, cool, yeah, but in this case it won't affect. Okay, cool. Now next thing is, let's do this. Okay, I'll explain what these are fairly quickly. Okay, this is the neural network that we'll create. Okay, input layer has to be 256 by 256. Okay, X, Y, and Z. Okay, so it's a let's say a 3-paged book of 256 by 256. Okay, one stands for R, the other for G, and the other for B. Okay, there you have your 3 channels. Okay, we get into convolutional layers. Okay, I'll show what this does. We get this thing, which is a kernel. Okay, this thing will fly by your image. Okay, what it'll do is this thing will be pasted here. 1 times 1, 1, 1 times 1, 1. Same thing for the other 2. And then the plus. 1, 2, 3, 4, 4. Okay. What happens if you have a 0 here? It'll be 1 plus 1 plus 1, because 1 times 1, 1. Same thing for the other 2. We get a 3. Why would we want to do a conv2D? So I have it written down here. It's for features, to enhance features, such as corners, edges, and stuff. So you downgrade it or downsize the image, but you still get a hint of where the edge is. An edge could be a little bit of this color, more color. Okay. Now, what is this? This is a transpose. The transpose works differently. This is not pasted right here. It goes like this thing kind of moves here. Okay. So it's this one will be touching this one. So you get a 1. Then it'll move 1. And now these 2 are touching this. This is touching nothing because it's over it. Okay. So you get a 2. Yep. So it works for that. Okay. We'll use conv2D. Okay. So that's what conv2D does. And we get the max pool. The max pool is basically doing this. We downsize the image. Okay. We kind of blur it a little bit, but we get the maximum pixel value. In this case, this is 1. Okay. This is 0. Okay. If you see, the image from 4 went to 2. So it means there was a kernel, a window of 2 by 2. Okay. So in this window of 2 by 2, give me the max number of the maximum pixel of this. It's white. It's this one. And this one, well, it's all black. So the 0. In this one, it's this color over here. We get it here. And in this one, it's this color over here. It's not the same one, which we get here. Okay. And that works for reducing computation, controls overfitting, and retains features. Okay. Overfitting is when you learn only in the test, but you don't do good in the training. I'm sorry, you learn in the training, you don't do well in tests. Okay. You learn that the flowers are yellow, like the example, but roses are not flowers. So, that's overfitting. Okay. And last but not least, we use flatten. Flatten is basically from our matrix, create one big long list. Okay, cool. That's what we're going to do. Okay. Model 1 equals TF Keras sequential, open parentheses because it's a function, and then this. Oh, what? No. There you go. Cool. Now, inside we'll say, or we'll design the neurons. Okay. First thing, input layer. So we have the Keras layers. The first one, conv2D. Okay. So it's careful with the capital letters here. Conv2D. There we go. Now let's get 32. let's do a 3 by 3 kernel. Okay, what was this number for? I don't remember. Wait a second. Oh, the filters. Okay, the number of filters. 3 by 3 kernel. The activation was what, bro? Okay. Cool. We don't have to create value again. Here it is. Like, it's super easy. And for the first layer, always do input shape. Okay, equals 256 by 256 by 3. There we go. That's it. Okay. Input shape equals. Cool. Okay, nice. Now, let's max pool this just to get a lesser dense image. Okay, so we'll get an easier image to work with. Okay, cool. So tf that cares the layers. That careful with the capitals. Max pooling to the okay to like okay, cool. Now here layers. Okay, the layers that are specifically in the middle. Okay, I'll type quicker. Okay, see if the carested layers that on to the 64 filters 1 activation equals should be value as well. Okay. Yeah, let's do max pooling again. Okay, let's max pool this. How did I come up with this neural network? I've read about them. Okay, so I've some with some like with TensorFlow, I took a course and I know how these work. Okay, so I'll just like try on error. Okay, so yeah, what if I add a max pool 2D? And this goes back to this question over here. Like, is it okay if we use our own neural networks, or just create like just use it other people? You have to spend a lot of time trying to come up with an architecture. Just use whatever someone else is using that guarantees that works correctly. Okay, cool. Now, sorry, and let's just get rid of this and in layers or layers. Okay, let's see. I'm running out of time. I have okay. Oh shoot. Okay, I'll copy paste the whole thing because we have to train too. It'll take time. Okay, and I'll just explain it to you while it's training. Okay, cool. It has vol data, what do we call it? Train data. There you go. Okay, let me just see if it's training correctly. Come on, you can do it. Yep, there you go. Okay, cool. Now, this will take... Oh, that's not good. That's not good. Okay. Cool. I know why. Okay, stop! Oh, my bad. Give me a second. Yeah. Okay. Let's change it to a GPU. Okay, let's go with the GPU. GPUs are really good with computer vision, okay? So, this means I have to restart the whole thing not from scratch, but I'll just need to reuse this one here, this one here. There we go. That's what I wanted and I needed. And I'll go back and run this one over here, this one over here. What we just wrote, we have to rerun it. So it runs on a GPU. Cool. Good. Now we'll do it. Okay, nice. It was going to take like 3 minutes per epoch. No. So okay, cool. Error? Where? Oh yeah, shoot, my bad. If you restart the whole session, you have to resubmit Kaggle. See? So for whoever asked the question, like, hey, what happens if I don't have my Kaggle JSON? Here I have, right? I cannot find. Yep. Okay. So if you omit this, if you don't do this, it'll throw an error from Kaggle. Okay. Yeah. Now I need this one from here, and okay, and this one too. There you go. Cool. So while it runs, okay, let me just walk through it. Okay, we have ReLU. Okay, these are the neurons. I'm sorry. The number of neurons. In this case, 128, 64, 64, and we have one last neuron. In this case, sigmoid. We need sigmoid because it's between a dog or a cat. The thing that gives us 0 or 1, the activation function is sigmoid. If you use ReLU, won't work. Or I think it works, but stay with sigmoid. The one that works too is tan-H. Let's just stay with sigmoid, okay? Cool. Oh, error. Where? Can a dog? Did I get this? Oh, wait a second. Import. Yep, I remembered. Yep, you stop. There we go. My bad. Takes more time. Come on, let's do it faster. There we go. Cool. So this is what it does, okay? It's sigmoid. So we get a 0, 1. From there, I want you to compile. I want you, because it's a binary, we have to use a loss function, which is the binary cross entropy function. From there, the optimizer will be Adam, okay? Adam is an optimizer used in CNNs, which are convolutional neural networks, with a learning rate, which is our alpha. In this case, 0.001. We don't need it that high, because Adam works with 0.001. Okay, cool. The metrics that we want to use is accuracy. Basically, what we did here, where is it? Here. Like these functions are basically inside TensorFlow, and you just call them like this. The metrics accuracy. You can call other metrics like mean squared error, mean absolute errors, but in this case we need accuracy. Okay. Steps per epoch. It means for every epoch, tell me how many steps. You just do a little bit of math here. Voila. Now we say model.fit. It means train. Okay. Train data. Epochs 10. Okay. We don't need more. Steps per epoch. The number of steps per epoch. The validation data is the training data. What? Wait a second. This is not good. Okay. There's a small error here. Oh, no way. Wait a second. It's not train data. What? It's... Did I call it train data? Yeah. Ah, shoot. My bad. We have two train data. Yeah, that was my bad. Okay. Yeah. In all data. All data. Oh, come on. Yeah, I was like, why is validation data training data? Okay, yeah, careful there. Because if not, then, it's the same test. Like you're training and testing on the same thing. It'll do great, but it's a lie. Okay, cool. Now it's training. Okay, I hope it doesn't take too much. It takes 9 seconds. See the difference between a GPU and a CPU. Okay, 9 more minutes. Okay, I'll copy paste some more code. You'll have this on GitHub later. Okay, but let's get here more code. Let's actually see how this performs, okay? There. So this is a function that basically gets the response. Oh, cool. So we'll use a URL, an image from Google, okay? Here I have an image from a cat, okay? We'll see it. And it'll get an image from Google, the URL that you give it here. So you can use the URL that you want. We'll open the image. Now the image as a numpy array, important. Resizing to 256, 256 won't work if you don't do it like that. Normalize the values from 0 to 1. Remember, neural networks love values from 0 to 1. And we expand the dimensions because in this case, the neural network likes this dummy dimension. Because that's how it works, okay? That's a tensor, okay? So it's batch number 1, 512x, 512y, 3 is RGB, okay? Cool. Now, we should print the shape. We do a prediction. If the prediction is less than 0.5, let's remember why. if the prediction is less than 0.5, it means it's over here. Let's assume it's a 0. If it's greater or equal, let's just assume it's a 1. TensorFlow by itself will decide if 0 is cats or 0 is dog. Okay. Oh, that's a good question. No, it's for free. Okay. So if you see here, these ones are more powerful, but they're grayed out. Okay. So these ones are, you have to pay for them. This one's free. Okay. Same for these two TPUs. Okay. Cool. Now, come on. Can you do it? 7 out of 10. Okay. Cool. Now, remember I told you, hey, about the small error that I had about the epochs. Oh, sorry, the steps per epoch here with the batch size. Okay, the thing is, it's wrongly calculated. So you can see some of them take 32 seconds, some of them 9. Okay, some of them 31, some of them 4. Okay, the calculation is not correct because the amount of images or the number of images, yeah, 8005 cannot be correctly divided over 32. Okay, so just find a number that fits the division and you're good for it. Okay, cool. Now, come on. It has to be. We have 5 more minutes. Can you do it? Yeah, it's okay. Epoch 10. Okay, there we go. Accuracy, you can see it went from 53% guessing. Okay, in this case, it's guessing because we have only 2 images. If we had 10 images like before, the first one normally should be 10%. Because out of 10 images, I got 1 correct. Out of 2 images, I got 1 correct, which is 50%. Okay, guessing, learning, unlearning a little bit, learning more, unlearning, learning, and some learning. Okay, you can add more stuff to it to say, hey, out of all of these, give me the weights and biases. Now you know what weights and biases are of this specific epoch. So don't give it this one or this one that it underperformed. Give me this one. So you can get the biases and the weights of this one and use the best, the best part of them all. Okay, cool. We won't do that now. We'll use this one, which is fairly good. Okay, and we get a cat. Okay, it's a cat. That's good. And see, just under the limit. Okay, it probably could perform a little bit better. Okay, let's do something else. Dog images. We have 5 minutes. Okay, I'll actually leave it up to you. Someone, whoever wants to do it, send me a URL of a dog picture. Okay, I'll put it here. Okay, so someone look for an image of a dog, send it to me, and I'll try it here. Okay. In the meantime, a question here. Okay, what were the optimal batch size? Does it depend on GPU? Yes and no. Batch size depends on RAM. Okay, so every single image, whenever you're training, is fully loaded on RAM. Yep. So RAM is the one that takes all of that weight. Okay. For you to optimize RAM, because GPU has to use RAM, the CPU has to use RAM, your computer uses RAM. What you do is do batches, so it feeds like small portions of the image, and voila. Yep. Same with the epoch. No, epoch is just for time. Okay, epochs is just like the time that you want to take to train. YOLO, I think it took like 1 week to train, or was it ChatGPT? One of those two. It took 1 week to train. Okay, so imagine that. Like imagine the expense. Imagine the time. It's a lot. Okay, cool. Thank you. Okay. Let me do, how can I do this? Oh, shoot, I can copy it. Oh, that's not good. I thought I could copy it. Can I copy it? Wait a second. No, I can't. Well, that's not good. Oh, that's unfortunate. I cannot copy the comments. I'm so sorry. I thought I could. I can't. Okay, my bad. I'll just do one here. Dog images. Wait, thank you for sharing though. I'll just get this dog over here, because why not? Let's open a new tab. Yep, there you go. This, copy, paste. I hope it does good. Oh, it's a dog. Just above. With more epochs, probably a little bit tweaking the learning rate, it could work better. It still works though. Let's see if we can make it guess something incorrect. So these are golden dogs. Make it, I don't know, like a, yeah, this one. Okay. So let's see if it doesn't see the pointy ears. Let's see if it can say safely, hey, this is a dog. Oh, cool. Actually, it kind of sees that this is a dog more than the last one. Why? Not sure. Okay. Okay, questions. Higher epochs means higher accuracy? Yeah. Okay, cool. So, first of all, I'll answer those questions. Let me just do this. Okay, so before I answer the questions, I have 2 more minutes. This will be on my GitHub, okay? My GitHub is Bully601. Okay, so later, like an hour later, just double check there, and all of these codes will be there. Okay. Cool. Higher epoch means higher accuracy. Yes, to a certain degree. Okay. The epochs are also, you can have, like, you have to think about it as how many times do you want your model to see the same image or the same data. Okay. So if you have like ChatGPT, you have a lot of data. Okay. You need a lot of epochs. If you have 10 images with 1,000 epochs, you'll overfit that. Yeah. So it kind of depends on the data that you have. Okay. Cool. Now, what if you give it a fox image to it? Ooh, let's do that. Let's do that quickly. Fox image to it. I guess it'll be a dog. Not sure. Come on. My internet is kind of weird today. Why? Oh, there you go. Copy. Paste it here. And voila. Oh, it's a cat. So it's a cat. For this, it's a cat. Okay. It doesn't know what a fox is, so it kind of just guesses. Okay. Cool. Now I'll just stop sharing for now. I'll do this. Cool. Lastly, if you haven't, go check in here, please. Great session. Thank you. Thank you for being here, for, learning with me. We learn together. And yeah, we have Wikipedia races with Wei. So if you, hey, Wei, if you're connected, go play with Wei a little bit with Wikipedia races. I'll be streaming at 22, which is 10 p.m. ET, okay, about an intro to Linux, okay, like how to use Linux and all of that, okay. Hey, thank you for chatting with me. Your LinkedIn, please. Yes. Give me a second. Do I have it here? No, I don't. Wait a second. Give me a second. Let's do this. Pen. There we go. Thank you, Billy. You are welcome, Quakers and Cheese. Nice to see you and have you in my streams. Great vibe. That's me. Serious. Yep. Follow me on LinkedIn. And yeah, so I'll leave you two with Wei. Thank you for your time. And yeah, see you in 6 hours. No, 4 hours. Okay. Have a nice one. Thank you. Bye bye.